But if I commute the order of the differentiation and the partial differentiation, if I make that switcheroo, then that's partial lambda of this guy, which is lambda minus 1 minus lambda 1 squared e to lambda x, right? Partial differentiate that with respect to lambda, and that gives me, well, it gives me a couple things. On the one hand, it gives me twice this, but then I get plus this quantity squared, and then derivative of this with respect to lambda pulls down an x e to lambda x. Now, I'm doing this with lambda equal to lambda 1, that evaluation at the end of all of it, okay? So remember, that's out here, that's out here. So after that differentiation is done, then I plug in lambda equal to lambda 1, and so that's 0, and we get 0. This is what I was forgetting to show you the other day when I tried to show you this. The thing that was missing from our previous discussion was the introduction of lambda 1 versus lambda. Basically, I had lambda 1 set equal to lambda, which made it really hard to understand, and frankly wrong. Or, well, anyway, this is better. So that goes to show you that if you have a solution which, when you plug it in, it generates an equation in a parameter, right? If that equation happens to be a repeated root, you can rewrite it as the parameter variable minus the specific root quantity squared, and then this same derivation will work with the frobenious solution, because like if I have a repeated root in the frobenious case, I can also do the same thing. I can write it as like, but it's more complicated looking because the indicial equations, well, I guess it's still r squared minus 2r1r plus r1 squared, which can be rewritten as r minus r1 quantity squared frobenious solution of r comma x. And then the derivative of the frobenious solution with respect to r, after we set r equal to r1, should then be a solution, a second linearly independent solution to the frobenious case of a repeated root. Excuse me. This is not in your book, okay? This is wisdom I share with you. I think I found this in Rebenstein, which is a phenomenal differential equations book, more or less at your level, but out of fashion these days. It doesn't have big glossy papers or tons of modern applications. It just has tons of correct mathematics written from a master. Why would we use that book? Let's see here. So like y2 is partial y. I mean, I wouldn't use it because it's out of print. Sadness. Anyway, y2 is partial y partial r, and not enough homework problems. Y2 is partial y partial r, then set r equal to r1 is what I'm saying from that general derivation. That's going to be another solution to this. Supposing that we have an indicial equation with repeated root r1. So you take the the r1 frobenious solution, and I differentiate with respect to r, and then I, well, I differentiate with respect to r1 basically. That's what it boils down to. So if you differentiate this with respect to r1, it gives you two things. On the one hand, it gives you log x times this stuff again, which is exactly y1 of x, right? And then the other thing it gives you is x to the r1 times this differentiated with respect to r1, which is just that. This is awesome, because this says in the case we have a repeated root, we just solve it once, and then we just use this thing to create the second solution. It's so easy, actually. All you have to do is differentiate the coefficients that you found with respect to the you just have to differentiate the coefficients with respect to n, basically. Yeah.
So you're saying, like, whenever we find our r values, they equal the same number as perfectly?
Yeah, like, let's see here. Hypothetical, if you... now, I still haven't answered your question, which is, what's so quirky about differing by an integer? So hypothetical, suppose you had r squared plus 4r plus 4 equals to 0 for your initial equation. So that gave you r plus 2 quantity squared equal to 0, right? So therefore, r1 equals to r2, so to speak, equals minus 2, right?
Yes, you just solve for R1 and then
So let's suppose we do the recursion and we find that the coefficients for the first Frobenious, the Frobenious solution of R1, are, let's say, n squared over n factorial times, I don't know, cosine of r. No, that's impossible. Let's see here. I don't know if that's impossible. It just seemed weird. Times r squared. Suppose that's how it worked out, all right? Plus 1 there, I can't stop myself. All right, then, in other words, y of x, y1 of x, comma, r1 equal to some, n equals 0 to infinity, n squared over n factorial, r squared plus 1, x to the n plus r, right? So there you go. There's your first Frobenius solution. It's saying the second one, y2, would just be the log, how's it go? You do log of x times y1, which is just this stuff again, all right? Plus, what do we do? X to the r1, which in this case would be x to the minus 2, times the sum, n equals 0 to infinity, and then you got to differentiate this thing with respect to r. I mean, of course okay, fine. I haven't quite done it yet. This actually should be, you do what? You set r equals to minus 2 when you actually write down the solution, right? But the point is, I'm writing it that way so I can differentiate it. So this differentiated gives me what? It gives me, why didn't I make it simpler? I'm an idiot. So r squared, there, that's better. Well, I'm just trying to illustrate the pattern. Why am I making it complicated? Okay, so 2rn squared over n factorial plus 1. I mean, the n stuff is just constants with respect to r. That, x to the n plus r. And then, of course, you set r equal to minus 2 after that's done.
so before we started this, there would be no way to come up with that answer just because if you did it twice with the same number.
Right now, yeah. If you just try the naive. Well, naive seems like a misuse of the word naive. But let's say naive Frobenius solution, that won't do it. You'd have to now. I think the way your book does this is he doesn't explain it this way. If you look at Theorem 7 on page 475, he has. It goes on 476. Let us count the ways. So let x naught be a regular singular point for y prime prime plus py prime plus qy equal to 0, and let r1 and r2 be the roots of the associated initial equation, where the real part of r1 is greater than the real part of r2. So he's allowing for the index to be complex. Great. But he's assuming that r1 is the larger root. Okay, assuming that they can be ordered, that they're real. Okay, so if r1 minus r2 is not an integer, then there exist two linearly independent solutions of the form like we started with today. All right, you just plug in the different indices. Great, good to go. If r1 equals to r2, then there exist two linearly independent solutions of the form. First one, like this. Second one, and he just writes down, he doesn't give you this differentiation result. He just says that y2 has the form y2 equals to natural log of x y1 plus the sum. Let's see right here. This is equation 14 on page 475. He just writes down bn. Oh, and I think he's doing this at a point x naught. So I'm going to skip his x naught. All right. So bn. Yeah, I mean, if I was doing it x naught, I should have log of x minus x naught as well. Okay, but I'm doing x naught equal to 0. So bn, x to the n plus r. He just tells you that that's the solution. It's of that template, and then you're supposed to go work with that and figure out the b sub n's. But this is inferior. This is much better, because this says you don't have to do work. Yeah, you have to do work, but it's the kind of work we love. It's called differentiation and evaluation. Now, it does require you to figure out, this is another reason, in fact, the best reason, the penultimate reason for finding the recurrence relation as a function of r as opposed to a specific index. Because if you find the recurrence relation for n in terms of the index, right, then you can differentiate it and you can evaluate it to get in the repeated root case. I mean, that's pretty sweet. But it's also the reason he doesn't write this, is because there are problems where it is too onerous a task to actually calculate the formula for a sub n of r. And so that's why your book writes what it does, is because sometimes you can't find the formula like this. This formula doesn't exist in the realm of our calculational prowess. And if that's not available, you can't differentiate it, right? So then you have no choice but to go back to this and do term-by-term battle. So that's why the book does what it does, and that's why Rabenstein does what he does, because Rabenstein is the master and he can calculate it. Let's see here. If r1 minus r2 is a positive integer, there exist two linearly independent solutions of the form. And then the first one's the frobenious solution. The second one is, it's almost the same, but in the case they differ by a positive integer, you get a fudge factor of c here then. So see this is what changes in the differ by positive integer. It allows for a constant here as well. And then finally, if the index is complex, what, he doesn't throw, what? Come on, no complex case? Well, I want a refund. Where's the complex case? Hey. Oh, he's relegated it to a problem. Problem 26, he shows you how to do the complex case, all right? But he has not put it in the body of the section. Anyway, I think we have done enough now that you should be able to understand section 8.8 if you want to read it. Section 8.8 on special functions tells you how to define so-called Bessel functions, hypergeometric functions. Have you seen these before? Haven't you ever tried something in Wolfram Alpha and have spit back something hypergeometric or Bessel or something? Like if you try to do certain integrals, it'll spit back functions that you don't know what they are. Many of those things are defined in terms of as a solution to a regular differential equation with a regular singular point. And the method of Frobenius is actually how we construct said functions. That's what section 8.8 is about, special functions constructed by the method of Frobenius. But anyway, I think I've told you enough about this. I don't test the method of Frobenius in the in-class test because it's just not reasonable, right? I mean, if I gave tests that were of the form, I meet you at 6 o'clock as I'm leaving, I give you the test, I say, okay, I'll be back at 9 to get it, and it's 9 in the morning, that would make it reasonable. But short of giving tests like that, which are probably going to cramp your style around here with all of your many social obligations, I wouldn't do it. It's for another time and another place. It's not for here. Anyway, that's it pretty much. So, oh, I'm sorry, I went over. I'll shut up. You can hit it.